Okay, let's take a look at one of the problems that falls into the category of multiple linear regression. Right, that's the quiz that we're going to have next class. So go ahead and load jump. All right, launch jump, and let's take a look at the problem that was supplied with the jump software. Okay, so for that, go to help and sample data library. All right, and in the sample data library, please find the file that's called bodyfat. Body big class, no, that's not it. Bodyfat, right there. Okay, supplied with the jump. Okay. What happens is a lot of times in the medical profession or in the sports, people would like to measure their percentage body fat. Okay, anybody had body fat measurement yet? You did? How is it done?
There's lots of different ways, but there's like a device that they can just pinch to different areas of your body.
Yeah, that's one way, right? You take the measurements, right? So your height, your weight, different measurements such as waist circumference, right? All these things, or pinch this place, right? They like have calipers, they pinch your biceps. Yeah, on the side, yeah. And another way how actually supposedly the most accurate way to determine percentage body fat is called hydrostatic weighting. Okay, so the general idea is that muscle and bone have high density, higher than weight, the water. Okay, fat has lower density than water. So therefore, depending on what percentage body fat you have, you will weight certain amount in the water, depending on the breakdown between the two tissues, right? So they weight you just regularly, right? And then kind of submerge you into the water, say exhale as much as you possibly can out of the lungs, right? And then take your, how much you weigh underwater, right? And then there is a complicated formula that basically tells the percentage of body fat. So that file actually is another attempt to build a model that will allow us to determine the percentage body fat based on the measurements, right? So let's review what do we have here. First of all, percent body. So we have 252 people in this sample, right? And for these 252 people, we know the percentage body fat. The first one 35.2, another one is 11.8, etc., right? And also we measure about each person age, how old they are, right? Weight in terms of pounds, height in terms of inches, neck circumference, chest circumference, abdomen circumference, hip, thigh, knee, ankle, bicep, and forearm and wrist circumference. So there are a lot of measurements that we're taking, right? So hopefully we will be able to construct a model that will allow you to take these measurements, right? So any person, really, okay? Take any person, measure a bunch of things about them, right? All kinds of circumferences, their height, their weight, their age, all of these things. Plug that into the formula and calculate from that percentage of body fat, right? Body fat. Okay, so here's what I'm going to do. The approach that I'm going to do. I'm going to throw all variables into the model right now, okay? And note that, by the way, what's my target? What's the name of my target variable? What's that I'm trying to predict? Percent body fat is my target, right? And everything else is predictor, right? Note that my predictors and my target, all of them are continuous variables, right? So there are a couple of ways how I can do that, correct? Let's see if I still have, no, I closed that. If you have continuous target and continuous predictors, one way to do it is to build a regression tree, right? Another way to do it is to build the multiple linear regression. And let's take this route, okay? Let's do the multiple linear regression. So go ahead and click on fit model. Click. Okay, so percent body fat I'm going to put right here as my target, and all the other variables, age, weight, height, all these things up until and including wrist circumference, these are going to be my axes. So I'm going to add them into effects, right? Okay, cool. And then I'm going to click run model. So here is my model. Well, let's take a look at the model first. So there are a lot of things going on here, right? First of all, let's take a look at the parameter estimates, okay? So essentially, my equation is right here, okay? So let me kind of try to write it out. So here's what I'm doing in reality. Percentage body fat, let me call it BF, okay? percent body fat. I'm trying to build a model that is using intercept plus first slope multiplied by, what's my first variable out there? I forgot. Age, weight, height, etc., right? Times age plus beta 2 times, whoopsie, hold on. What did I do? Okay, beta 2 times weight plus beta 3 times height plus I have a bunch of other variables, right? I have about 10 or maybe 15 of them, right? So essentially this table, parameter estimates, it gives me all my parameters that I'm needing, right? So this is my intercept right here. Okay, then age, how does age affect the percentage body fat? In what way? With age it goes up or goes down? Goes up, right? Weight. Weight affects things negatively. That's a little weird, right? The more you weight, the less percent body fat you have. That's a little fishy, right? Something is wrong, right? So first of all, let's kind of clean up the model a little bit, okay? Let's see if we can get it to be more realistic. So first of all, what I'm going to do is, remember how we approached that? First, we tested the model for overall validity, right? So test overall model validity. Overall model validity. That is a V, okay? So here's what I'm doing. Just to test model altogether, right? Bird's view kind of test, okay? My null hypothesis, I'm testing this. That the first slope, and the second slope, and the third slope, and all of them, right? All slopes, whatever is my last one, number K. Well, actually, let me put number P, okay? P as number of predictors, right? Number of independent variables in my model. All of them can be set simultaneously to 0. In other words, I can take this model right here, okay, and set all the slopes to 0, and if I do that, essentially I'm taking out all of my independent variables out of the model, right? I'm saying that no model is just as good as this model, okay? So in other words, if null is true, then I'm going to say that my model is not statistically significant, right? Is not valid altogether, okay? And alternative is going to be that at least one, right? At least one of my slopes, beta I, has to stay the way it is. That's what I'm testing, okay? In order to take a look at the model overall. Not looking in specifics, kind of bird's view, right? Is that a good model altogether, or is it a bad model? Because if I find in favor of null, that's pretty much where it ends, right? If null is true, then that's it. I don't have a model. We can relax and move on, right? Okay, so where do I have the hypothesis test for that? Let's take a look. I'm looking for the p-value, right? I don't have it here. So regression reports, it's actually coming in the analysis of variances. For some reason it didn't show up by default. Analysis of variances, and where is my, yeah, here, analysis of variances, right? So remember we looked at that in the previous class, right? It computes the F ratio. I'm not going to go into the details of what that is. And probability greater than F using the F distribution is your p-value, okay? So here, my p-value is so small, it's less than 1/10 of the, actually 100th of the percent, right? So what do I do with this p-value? P-value is, let me put it, 0.0001. It's less than any reasonable value of alpha that I can possibly use, right? Less than 1%, 5%, 10%. What happens if p-value is less than alpha? What do I do between null and alternative? What do I pick? Reject the null in favor of alternative, right? So I reject the null in favor of alternative, and my alternative says that at least one of the variables that I selected as predictors is valid. Has to stay in the model. Therefore, model is not complete bust, right? At least something is going on, okay? Well, now let's discriminate between different variables. Let's see which ones are important and which ones are not so much, okay? So I'm going to test individual predictors, okay? So test individual predictors or regressors, right? Predictors. And here's what I'm testing, okay? My null hypothesis is that this predictor, every one of them, is equal to 0, right? And the alternative is that this specific variable that I'm looking at the slope is not equal to 0. So if I find in favor of null, that means that the variable I, variable number I, is significant. It does contribute to the model, and we can't just discard it, okay? And here is not significant, right? Is not significant. Okay? So, once again, right? To test hypothesis, you need to find the p-values. Okay? So, p-value is less than 0. If p-value not 0, alpha, right? If p-value is less than alpha, you reject the null in favor of alternative, and you find that the variable is significant. So what I'm looking for really is small values of p, small p-values, right? Small values of p-values. Okay? So anything less than, let's use 5% as my cutoff point, okay? Any p-value which is less than 5% tells me that this variable is significant because I rejected null in favor of alternative. Anything higher than 5%, I keep the null, and null says, may as well throw it out. Variable is not contributing a lot, okay? So, let's take a look. Where to find the p-values? You remember we did that in the previous class. Where I have my parameters of the model listed, the intercept and all the slopes, the last column probability greater than t. That's p-values, okay? So, what do I see? The only p-values that are less than 5% are the ones that correspond to neck circumference, right? That's important variable. Then I have abdomen. Then I have forearm, and weirdly enough, wrist circumference, right? Who would think that measuring wrist circumference would tell you anything about percentage body? But that's what it is, right? That's what my model tells me. So all these other things that we thought about, such as, for example, weight. Weight's supposed to be important, right? Well, and that probably explains why my weight, slope for the weight was negative, right? That means the heavier you become, the less percentage body fat. That doesn't make sense, right? Well, here's your answer, okay? The reason why this, that was our result is, it turns out to be not a significant variable to begin with, okay? So I can actually get rid of the majority of these variables, right? But before we do that, let's discuss how accurate my model is, or better to say, how closely it fits the data, right? So let's take a look at the goodness of fit measures, all right? So I'm going to go into the, it doesn't show up right now, so regression report, summary of fit. If you don't see the R² portion, that means that you need to show it, okay? And it's in the red triangle menu. All right, so summary of fit. Did we discuss in the previous classes R² versus R² adjusted? A little, probably, right? So, question is, which one do I use, right? And basically, the big idea here is that R², and I told you that before, right? If you start throwing more variables into the model, what will happen to your normal, regular R²? It will always go up, right? So no matter what you do, you add some things that are completely irrelevant for your model. They have nothing to do with percentage body fat, okay? Like your sight, for example, right? Vision, you know, whatever number it is, okay? You throw it into the model, your R² will tick up, okay, a little bit. So therefore, the statisticians or whoever is building the model, business analysts, they would be inclined to throw as much garbage into the model as possible because your R² goes up, right? So therefore, we have to keep the reasonable balance between how many variables you have in the model and how accurate you want it to be. So therefore, what statisticians did is they designed another measure which is called R² adjusted. Okay, adjusted. And I'll write down the formula, but that doesn't make much sense, quite honestly, this formula. So n minus p minus 1 times 1 minus regular R². So what happens with this in this formula is if you start throwing more and more variables into the model, your R² will go up, right? But at some point in time, at certain level, a certain number of the predictors that you throw into the model, that measure will start punishing you. Why? Do you see that P right here? P is the number of predictors, okay? So the more predictors you throw into the model, the higher the number P becomes, okay? So therefore your R² adjusted starts to go down. Your R² is still going up, okay? You throw another junk variable, bam, r squared goes up. But adjusted r squared will start declining, okay? Because your addition probably that you make to your r is not going to be significant. So r essentially is going to stay the same. But because you're dividing by p, every next variable will get it lower and lower and lower, okay? So adjusted r squared essentially is the most preferred measure. So question becomes like, what do we use? Regular r squared or adjusted r squared? The answer is, for the simple linear regression, when you have only one predictor, it's almost the same thing. There is not much difference, okay? But if you have multiple regression, then that would be the weapon of choice, adjusted r squared, okay? Because it punishes you for making things too complicated and possibly using noise variables that don't contribute to the model. They create a fake impression that the model is getting better, while in actuality you're overfitting it, right? You're throwing more and more variables, adding more and more noise, and saying, oh, look, my r squared is growing. No, okay? It's growing not because of there is something really going on, just because of statistical trick, okay? And adjusted r squared takes care of that. So let's take a look at what happens in our case. Look at that. My r squared, the regular, my good old friend r squared, says that all these variables taken together, right, explain their variability from person to person in terms of height, weight, all kinds of circumferences, right, their age, different variabilities from person to person. They explain about 74.9% of the variability in terms of body fat from between different people, right? So these, how many I have, like 10, 12, 13 variables, right? They are responsible for about 75% of the variation. But look at what happened with r squared. R squared says, nah, not so fast, okay? I'm going to punish you because you throw in a lot of junk at me, okay? A lot of variables that have nothing to do with body fat, and therefore it's not that rosy actually, okay? So we're using r squared, and difference here is not that huge, right, admittedly. It's only, what, like 1.4%, right? But still it starts to go down. And if you add another variable, and then another variable, and there is a very weak correlation with body fat percentage, okay? Then r squared will go down even more. So it starts declining, indicating to you that, hey, you did too good of a job fitting the model, okay? We don't need that much variables into the model. Start taking them out. Okay, talking about starting taking them out, we just discovered that there are, out of these 15 or so variables, what are the important ones? The important ones are neck circumference, right? Because of the p-value less than 5%. And then there is abdomen circumference, and there is forearm and wrist. Everything else has high p-value, which means that if I take them out, will my model suffer significantly? No, right? Well, let's try it. And let's remember these numbers, right? I have about 74%, 75% r squared, and 73.5 adjusted r squared. Michael?
So just like make it clear, for this multiple, and we only look at the adjusted one, like that's the value.
Yeah, r squared, I mean, you can take a look at r squared, right? Nobody tells you, hey, Michael, don't look at r squared. Forget. No, you can look at both of them, right? But adjusted will kind of tell you that, hey, yeah, accuracy is great. But when you start seeing like significant decline, right, compared to your r squared, that's how you know that it's too much, right? Too many variables. Model doesn't like it, okay? So therefore you have to simplify it, right? We want to build models that capture essential things that are important, right? That contribute to the body fat percentage in this case, right? Everything else we want to keep out, right? And that actually boils down to usability of the model, right? If you make model too complicated, it becomes bulky, cumbersome, so we don't want that to happen, right? We want to keep essential things that explain pretty much most of what's going on, right? Yeah, so look at adjusted r squared, yeah. So I'm going to rebuild this model, okay? So let me put that thing down, minimize it, and let's do it again. But this time around, I'm going to pick only variables that my previous model said were important or significant, right? So obviously, I'm going to keep my percent body fat variable as target, right? But I'm going to now pick and choose, right? Neck circumference, then abdomen was also important, right? And then what was another, oh God, I can't remember. Forearm, wasn't it? Forearm and wrist, right? So forearm and wrist circumference. Is that what it was? Hold on. Yeah, forearm and the wrist. Okay, cool. So where is my thing? Right here. Okay, so now let's go ahead and run the model. And let's go back to the r squared, right? And adjusted r squared. Did we lose a lot of accuracy? after we removed the majority of the variables, did our model lose a lot of accuracy? Not a lot, right? We went from 4.9% in terms of R squared to 71.3, right? I took out like 10 plus variables, right? You would think there's going to be a gigantic drop. No, not happening, right? Why? Because these variables were not significant, not contributing a lot. They were noise that I was throwing in to overfit the model really. And look now at my difference between R squared and adjusted. Before that it was like 1.7%. Now it's less than a percent, right? It's actually close to 0.4, right? So now they start to converge together, right? So now my R squared adjusted is not punishing me all that much, right? It's almost the same as my non-adjusted R squared, okay? All right, so, well, let's take a look. Did anything change? I'm going to do the same exact thing, right? I'm going to look at my parameter estimates and say, hey, look at that. Neck circumference, is it important or not? Based on my p-value.
Yes.
It is significant still, right? Abdomen. No. It is, right? Forearm. No, forearm is not significant anymore, right? Okay, and wrist is still significant. Okay, let's take out forearm. So I'm going to build yet another model. So see what I'm doing? It's called actually stepwise regression approach. First thing first, right? And there are two ways to do it. There is a forward stepwise regression, there is a backward stepwise regression. Forward means that I'm going to add one variable at a time and see what happens, right? Backward means that I'm going to throw everything against the wall and see what sticks, kind of thing, right? And then I'm going to start things out, take things out, okay? So what we're doing really is a backward stepwise regression approach, right? Throw everything and then take things out to keep only important stuff, okay? So let's go ahead and build third iteration of our beautiful model. So I'm going to put that thing down, minimize it, and let's do yet another one of these things, right? So percent body fat, kaboom. Oh, God, what was that? Neck, abdomen, which one did we take out? Forearm, and therefore wrist is still there, right? All right, let me go ahead and run the regression. What happened to my R squared? Did it go down tremendously? And adjusted R squared? No, almost nothing, right? It was 71.4 and now it's 71.07. So my R squared almost didn't move, right? Adjusted R squared, same thing. Okay, and my model tells me that all of these variables are what? Significant or not? They are significant, right? So I'm kind of down to the bare bones, right? To the bare bone model, okay? That predicts about what? 71% of the variability in terms of body fat between person to person based on all these three measurements, right? One last thing that I want to point out is we may still be able to take some things out. How do I approach that? Well, first of all, let's take a look at the residuals. Remember we discussed that. You have to look at the residuals plot. Why? Because the residuals plot can tell you if things are okay or maybe they're not okay. What kind of residual plot is the best? The one that has homoscedasticity, right? Homoscedasticity, meaning that it's a random cloud of points, right? With no curves, no lines, no trends, no patterns, and it's uniform, right? If you look at a cloud at different points, it has the same spread, right? So here's my cloud of points. It has the funky colors, right? Rainbow colors. I don't know why. Probably because the original points were colored for some reason, right? Do you see anything problematic with this plot? Or is it more or less PDG? Pretty darn good. It's PDG, right? It doesn't have heteroscedasticity, it doesn't have any patterns, lines, or anything quite like that. Okay, what are we testing the last? So, how cool is my residuals plot is one thing, but another thing that we need to look at when we're dealing with multiple regression is something that's called multi-collinearity, right? Remember that? Variables that are independent from each other, supposedly, they are truly independent from each other. And how do I do that? Well, let's go back, right? So here, I have abdomen, circumference, wrist, and neck, right? All these are my variables. I need to go to Analyze menu and do the multivariate methods, multivariate option, right? Click. Okay. So I want to cross-correlate all of them with each other, right? That's the idea. And if any of the correlations is high, that means that I have multi-collinearity, right? It can be high positive or high negative. So any independent variables that are highly correlated with each other is a problem. Why is it a problem? They tell me essentially the same story, right? Like, for example, age goes up, mileage goes up on the car. Oh, yeah, true. So if they're correlated, then why do I keep them together? They kind of show me the same thing, right? So let's do that. Neck, right, was one of them. What was, my God, abdomen, right, another one. And was it wrist? The three ones that we boiled down to? Yeah, okay. So I'm going to add them to the columns and click OK, and it will give me the cross-correlation matrix, right? Mutual correlation. Okay, so again, am I looking at the diagonal numbers? 1, 1, 1. No, right? Because it's a variable with itself. It's always 1, right? So I'm ignoring the diagonal. Okay, so what do I see? Neck circumference is highly correlated to the abdomen, right? Because it's 0.75. Neck circumference is highly correlated to the wrist, right? It's 0.7, almost 5. How about abdomen with the wrist? Is it a high correlation or is it okay? It's okay, right? It's kind of pushing the boundaries, right, close to 0.7, but that's okay. So, can I eliminate things even more? Neck probably, right? Because neck is highly correlated with everything else, right? So let's try taking neck out of the equation, right? So, I'm going to put that thing down and run yet another model. Now without neck circumference, okay? Let's try that. So I take percentage body fat. What was that? Abdomen, right? My effect. And the wrist, right? So I boiled down all of my variables, only to 2 of them, okay? All right. So let's go ahead and run the regression. And what do we see? Where is my goodness of fit? Here, summary of fit. What do we see? Did the model lose after I eliminated neck circumference? No. It's actually practically the same, right? And that's basically the idea, right? Our p-value told us that neck circumference is important, right? But the correlation matrix said it's actually highly correlated with everything else, so it's kind of telling you the same story. So if you take it out, probably nothing is going to happen. And indeed, that's the case, right? We take out neck circumference, model practically stays at the same level, okay? So that's pretty much my final product, okay? Only 2 variables out of 15 that I had. Only 2 variables turned out to be important, and that gave us very, very decent accuracy, right? Goodness of fit measure. Okay? All right. So let's end this class right here.